So good morning everyone, I'm Dario Billi, I'm from Strasbourg and the University of Pisa, and I'm presenting today on behalf of my colleague Chaimaa Delasse, who couldn't be here due to some issues. The work I will present is entitled In-Situ Gaussian Splatting, 3D thermal mesh visualization and urban tree in augmented reality. So why thermal tree monitoring of urban trees? Actually because urban trees cool cities via shade and evapotranspiration, but need 3D assessment for health and water stress. The thermal infrared can reflect plant water status and is useful for monitoring them. The current workflows are mostly 2D, desktop-based, and hard to interpret or share. This creates a gap between the data capture and on-site understanding, which these works aim to address. The research gaps that we identified are three main gaps in the literature. First, Gaussian splatting had not been applied to thermal vegetation imagery, which is low texture and difficult to reconstruct. There is no evaluation and validation of Gaussian splatting thermal mesh against TLS reference for trees, and there is no field deployable augmented reality for in-situ 3D thermal tree viewing. So our contribution would be just to first train and test MILo Gaussian splatting reconstruction from 3D images of an urban tree. Second, a geometric validation plus thermal validation against Z+F TLS with color mapping version, and an hybrid markers plus GPS Android augmented reality for in-situ canopy thermal viewing. Let's move now to the data acquisition campaign. The campaign took place in the country yard of Palais Universitaire in Strasbourg on a single circle window with acquisition by camera FLIR T560 with an amount of 112 TIR and RGB per image. The reference is a Z+F IMAGER laser scanner and a T-cam mounted on it, with a total of 5 scan stations. Let's move now to the pipeline overview. The pre-processing consists on the acquisition of the TIR image and the JPEGs and the RGB image, of course, with the standardization of the FLIR Research Studio, fixing the scale from 10 to 40 such degrees, with a consistent felt color image. The reconstruction laid on the extraction from motion with the RGB pair master and slave camera, and from this input we feed the MVS reconstruction to achieve a mesh reconstruction, but also with the same input we feed the MILo Gaussian splatting pipeline in order to achieve both together in one shot a radiance field and an iterative mesh extraction. So at the end we will have a mesh that we will compare with the MVS reconstruction against TLS and a radiance field, which will be used for augmented reality visualization. Planned on Unity 3D GS.ply viewer Android, using a hybrid anchoring plus Buforia markers and GPS that can allow us to have an in-situ field visualization. The validation, so it will be a geometric validation using M3C2 based on cloud compare against the TLS, and a thermal validation with the color mapping version against the T-cam. Now here, just proper to show a little more on reconstruction. As I said before, we leverage on SFM using the technique of RGB master and T-slave via inter-of-sensor offset. And as you can see, MILo Gaussian splatting can provide us radiance field trained together with the extraction of a differentiable mesh from this radiance field at each iteration. Now we move to the geometric validation. The geometric validation, as you saw it since the beginning here, the time processing is very different from MILo compared to MVS. But of course, because MILo is training jointly together a radiance field plus a mesh, while the MVS just extract directly a mesh from the FM. What about the number of points? Also the number of points here is much more higher for MILo, so it's like a synonym that MILo provides more geometry. But after we will see in the qualitative analysis. The mean is more or less comparable, the same for the standard deviation, and another interesting metric is the percentage of outliers, which is quite similar for the RGB data of both pairs, MILo and MBS, but for the thermal imagery it's much more higher for MBS, with a mean that the MBS can produce some reconstruction but with a lot of very high noise. And so we move directly to the qualitative reconstruction. This is the RGB. As you can see, it's quite similar for both results outputs, MILo and Metashape. But if we move to the thermal imagery, as you can see here, the quantitative metrics can confirm what we see also in qualitative way. MILo has a very proper reconstruction and complete as for the RGB, while MBS struggle and fail. Now we move to the thermal validation via color map. So we have to take the RGB mesh information from the false color on the thermal mesh built on MILo that we decided to use to compare this validation, and to extract from the RGB back the information of the Celsius degrees. How we did it? Using a LUT inversion, sampling 2048 points recovers per vertex and from RHC color palette. And what we saw actually, the mean absolute difference of the accuracy, we reached 0.7 Celsius degrees against the TCAM reference, which is within our threshold of plus and minus 2 Celsius degrees. But if we go more deeper in the distribution of the key S, we have a moderate agreement, as you can see also from the graph plotted over here. And we saw that the bias is spatial, not by the calibration error. In fact, from the graph EC, you can see that for the vertical analysis, we reach a difference, a point difference on plus 3.3 Celsius degrees at the trunk base of the tree. And this we justify by the fact that we had a close range camera lens samples with warm sunlight bark. The same behavior for radial analysis on the graph BD, where we had a minus 3 Celsius degrees in the outer canopy. And this maybe is due to the fact that the acquisition by camera has been terrestrial and we didn't integrate a UAV acquisition also from the top of the canopy. So the scanner sees more angle than the camera in that case. Now we move to the in-situ augmented reality that we developed. We use a viewer Unity 3D using the thermal PLY at runtime, and we proposed a market-based tracking using Euphoria that can be useful for inspection in not in situ, okay, and to analyze the radiance fields used and comes out from MILo for inspection in also laboratory. And also we propose a GPS-based georeferenced model in situ, so you can open the app and see the model georeference in place, but of course with some limitation of offset due to the low accuracy for GPS by mobile phone. So the main takeaways and the limitation is that the Gaussian splatting is viable for text support tier where MBS fails. We had a proposal of semi-quantitative thermal fidelity within instrument accuracy, and the thermal Gaussian splats can be deployable on consumer phones. The limitations are that we had achieved and used a single tree acquisition date. We had also a temporal gap between the TLAS and the TCAM that catch the information of the ground truth, and still MILo is kind of heavy and so not yet on device. A working proof of concept, we also propose the augmented reality application to show to high school students to show how trees shape the urban microclimates. And as a future works, we want to try to implement the temperature as learnable for Gaussian scalar, a wider angular or UAV capture acquisition to cut the radial bias that we saw before, and multi-temporal and multi-species monitoring, so application to other additional datasets, and for last part, a cloud Gaussian splatting reconstruction that can be fully in situ workflow. Thank you for your attention, and if you want to contact about more the part of the thermal work, you can contact my colleague Chaimaa Delasse, which is the main author of this work. Thank you so much.